Hello. So we have a short announcement from Travis Goodspeed, who will also introduce the next talk.
Howdy do. So, as is the tradition at REcon and a few other neighborly conferences, we have the International Journal of Proof of Concept to get the fuck out. This is release number 12. We zero index, so this is our 13th release, and I believe our third or our fourth at REcon, which is always generous enough to print these for us and to ensure that the printing is good. They're by the registration desk. Just swing by and grab one, but don't ask for permission and don't slow down, and dear God, don't mob them because their job is hard enough. The next talk is by David Carne, a buddy of mine from way back. Oh God, it has been that long. Yeah. So he's going to be telling you how to reverse engineer a black box instruction set. And by this, it's not like an instruction set that you don't know. This is one that nobody knows, but for which you have an example binary and the ability to make changes and observe the results in that binary, and nothing else. So, without further ado, David Carne.
Thank you. There. I'm on VGA right now. The HDMI wasn't detecting. Nothing? Okay, 1 second. All right, well, let's see if I can get it not mirrored. Otherwise, I won't have my speaker notes, and that won't go so well. There we go. All right. All right, so as Travis most kindly introduced, my name is David Carne. The talk I'm doing is reverse engineering instruction encodings from raw binaries. And this talk came about because I was doing some hardware reverse engineering on a custom core, and a number of my software reverser friends were asking about how does one approach a problem like this. And so I don't have any fancy awesome software release for you today, although I will be putting the disassembler and assembler that I'm talking about here up online, but it's not that cool. The target isn't that cool. And all the techniques that I'm going to be talking about are relatively well known, but a lot of people apparently haven't seen them before, so hence the talk. In fact, they're so well known that on Monday I was telling some friends on IRC about the talk I was going to be doing, and they said, hey, didn't someone do something just like this at REcon 2012? And much to my dismay, it turns out they did. So I'm going to begin with a citation to Chernov and Trozina with REcon 2012, Reverse Engineering of Binary Programs for Custom Virtual Machines. And while I'm on the subject of citations, I'll also mention FX of PhenoElite, building custom disassemblers, which was presented at 27C3 for reversing engineering step 7 stuff. But my focus, as opposed to those two, is going to be more on microcontrollers and low-level systems, things that are directly coupled to the hardware and where they were built for a custom reasons because they needed custom hardware functionality as opposed to trying to deter analysis or to have a custom bytecode. And life's a little bit different down at those low levels. You find interesting things that you don't find in standard VMs. And in particular, this target that we're going to be looking at today is not really amenable to a lot of automated analysis techniques or wide statistical techniques. The plain text or image size that we have is just so small, and the fact that it's a mix of code and data tends to really reduce the signal-to-noise ratio for any kind of bulk statistical or bulk guess and test automated method. So today's example, I'm going to talk about a couple techniques. The first of which is cheating, because there's no point in reverse engineering an entire custom core just to find out you've discovered the 8051. Second is using a firmware structure to your advantage. And then I'll touch briefly on static techniques and then followed by some dynamic techniques. And I've only got a 30-minute slot, so I'm going to be moving really, really fast and covering this at a very high level. If you want to know more details, please pigeonhole me after or at lunch or something like that. And Chernov and Trozina covered the static techniques very well, so I'm going to just sort of cover one example of recovering code flow from that. So today's example is the ADF 7242, and that's an RF transceiver IC. It's made by Analog Devices, and the family includes sort of multiple variants for different frequency bands. And inside of it is a custom core that interacts directly with the RF hardware, and it's interesting for some reasons I'll talk about later. But first I should mention that reversing this has no particular importance in the security scheme of things at all. So I'm not claiming this is an important security finding by being able to reverse engineer or break this. The only point of interest for going after this thing is I originally started on it because Mike Ryan was interested in using this for a better Zigbee sniffer. And it's interesting because it can be interfaced with a computer with only a low-cost SPI cable, like any FTDI cable that you might have laying around. And since you can execute firmware on the chip, you can do real-time operations like real-time selective jamming or real-time channel hopping to follow a channel hopping transmitter without having to deal with and compensate for USB latency. And of course, finally, it's interesting because it exists. It's and a binary out there that's in a custom instruction set is sort of reverser bait. So as part of this project, I created a disassembler for the ADF 7242 and the similar families, and I'll post it later for anyone that wants it, if there is anyone. So the first hint we have from the datasheet is that the radio control and packet management of the part are realized through the use of an 8-bit custom processor and embedded ROM. And this is about all the information we have about it. That there's a packet manager with a processor, that it addresses 2 memory spaces, which is a program RAM and ROM in one memory space, and a bunch of data for various uses in the other. So that brings us to technique 1, which is cheating. And as a rule of thumb, until proven otherwise, a custom core isn't custom. Most of the time, it usually just ends up being an 8051, a Tensilica Extensa core, or a Synopsys ARC series core. And the Extensa and ARC cores are really commonly found because they allow a processor designer to sort of check a bunch of options and have a core created for you that you can synthesize in your product and get a tool chain that knows how to use it. They support adding custom instructions as well, but they're based around a common core that, Hexrays has a disassembler for some of it, I believe. There's definitely disassemblers out there for some of those, and those serve as a starting point for 99% of what you'll need. And of course, you have your friends binwalk-A, which can sometimes identify an architecture for you if you're lucky. Strings is great, datasheet press material. Don't neglect this stuff before you dive right into the fun technical work. And it is, as an example of why strings is better than one might think, there was a DSP that I was looking at once upon a time that was effectively a black box. This chip, you just gave it a blob that the manufacturer said you had to. And they mentioned Extensa, which tells you it's an Extensa core, that it uses the Vectra DSP instruction set, as well as the RTOS it uses, so don't neglect the simple stuff. But back to the sample that we have. We have a datasheet for the part, a loadable firmware module, and an app note describing what that loadable firmware module does. So that loadable firmware module extends the functionality of the 7242, so it does things like implementing addressing filtering. So it can automatically say, hey, this packet coming in, is this one that's of interest to the processor? Does the CRC match? Is it of a frame type I want? Okay, then interrupt the processor, but not otherwise, so it's great for low power modes. And this loadable firmware module we have is only 1369 bytes. So it's a very small sample in terms of having something to look at to figure out how it's behaving. And what we want to know is, first of all, what kind of machine are we dealing with? Is it a stack machine? Is it a register machine? What are the data path sizes inside of it? If it's a register machine, how many registers does it have, and how large are they? We'd like to know whether the operands are, or the instructions are register to register or memory to memory. we'd also like to know whether the memory layout is one unified address space that covers everything, or whether it's separate address spaces for those two blocks that I described before. And we actually already have some hints from the diagrams that we had that I'd shown before. And one example is that it showed an 8-bit data path coming from the program ROM. And that right away tells you it's probably not a processor that's using a weird, for example, like the PIC series 14-bit instruction word. Because if you're building custom silicon, and if we assume the datasheet is telling the truth, there's no reason to actually use an 8-bit path from the ROM when you can just use a 14-bit one just as easily. So before I go on to the next slide, does anyone here remember bank switching code? Is anyone unfortunate enough to be still writing code for something that does bank switching or requires it? I guess there's a couple of us here, but I guess most everyone's lucky. Bank switching is when you swap a bank of memory in and out because the processor address space isn't large enough to encompass the entire code that you want to run on it. And that shows up really, really well when you have a firmware file. For example, in this image that I'm showing you right here, you can see regular structure at power of 2 boundaries, and that's a real clear indication that whatever target you're looking at is using banking of some kind. A good heuristic is to count the number of zeros or Fs or repeating bytes right before power of 2 boundaries, and the lowest power of 2 that has that is probably the one that you're seeing banking occur at. But actually, these days compilers have gotten so good at allocating code in these situations that I had to sort of beat the compiler over the head to make an image that would show up here. So I recommend the heuristic method rather than visually. But there's other structure in firmware files that we can use to our advantage, and that's that they have to have entry points. So this is a loadable module. It's not a piece of firmware that runs right on the microcontroller, so it might be a little bit different. But still, either the ROM that's going to be talking to this loadable module, or if it's just firmware for the raw firmware for the processor still needs to get to the part of the code that you want it to execute. So it's a very common feature, and you actually heard some of this being talked about in the last talk, to have a vector table. And the vector table tells the processor, hey, here's where you're going to execute in the case of a certain instruction, certain interrupt, or for example, at reset. And it's very common to have this at the start or the end, and sometimes this table takes the form of a number of instructions that will perhaps jump to the code, or it might be a tightly packed table of addresses. And I did a brief survey of a handful of randomly selected embedded architectures, some of which are common, some of which are less common. And as you can see, the vast majority allocate a contiguous vector table at the start or the end, with the exception of one which actually only ever boots from a bootloader, so it's a bit different. Some of them can relocate it after the start, but it still needs to be at a fixed point at power on, which is generally one of those two places. Usually it's tightly packed, so it's not spread out over the firmware. It's usually tightly packed at one end or the other. And as I mentioned before, some of them represented as addresses, others represented as instructions. And if we go back to our sample, and this is the first time I've showed you the actual sample we had, well, what do we see right at the start of the file? It's a pattern of sort of what I would call stride 2, a stride 2 pattern right at the start. 2-byte chunks that are self-similar on a 2-byte boundary, followed by a series of 3-byte chunks that are similar on that pattern. And if we assume that all of this is a vector table, well, it'd be a bit of an odd one, because you don't normally see a vector table that has different sized elements in it. It would be harder for the processor designer to implement. So let's think about what we know about vector tables. Well, if it's addresses, probably doesn't make sense. We'll just look at the first part. Because if we look at those as big endian encoded addresses, well, they only differ by a single byte for each value, so that can't be branching to meaningful code. Or if it's a little endian encoded address, then they're spaced by OX100, or 256 bytes, and then it runs off the size of the module we just loaded, so that can't be a sensible explanation either. And that leaves instructions for the other option. They probably aren't absolute jumps, because we'd still have the problem about how you encode the jump destination. But what if they're relative jumps? And if these are 2-byte relative jumps to a 3-byte instruction, perhaps an absolute jump, then that would actually make sense for the 1-byte difference, because relative jumps are usually added to the program counter in some way. And that turns out to be exactly what the case is for this particular processor. It's a 2-byte relative jump to a 3-byte absolute jump that goes somewhere else in the program. And this is a trampoline pattern. It's very common in embedded systems, means the same thing as trampoline in any other system you've looked at. It's one jump through another to get to the final destination that the first may not be able to reach. And if we look at the last few bytes on the absolute jump, well, we can start deciphering those as well. The lowest 12 bits all seem to differ, and they actually end up having address values that all point within the firmware module that we've loaded. They're all within the size bounds of what we're going to load. So this makes sense. It's a good sign we're on the right path. But we can be a bit easier than this. Rather than trying to reverse it or analyze it from the bit patterns, the simplest approach is just to make a histogram. Just take the last 2 byte values and plot it on a chart and see where they go. And you get sort of a two main groupings in this distribution. And you see they're spread out over, at sort of around 0 and around the 32K mark. And you look at something like this and you say, well, I really don't think that this processor has a 16-bit address space. There's no need for it to be using the full 64K of address space. What's probably more likely is that the 15th bit, is actually a selection. It differentiates between 2 different instructions that both take an absolute address. And so the hypothesis is that the 15th bit is part of the encoding, not the address. And if we follow that hypothesis, we see something that looks much more reasonable. And I want to emphasize, I forgot to mention earlier, these histograms are of all byte patterns that match, that start with an OF byte. And so that's is basically based on every single OF sequence in the file, and it's a very small file, so you don't see a lot of noise. Normally you'd have a lot of random noise on the baseline, but this is such a small sample that you don't see it. So this is all things that match. And you see it collapses right down into a nice distribution, and that's all within the address space of the program ROM within the size of a potential program ROM plus the loadable module. So we have a pretty good guess at now relative jump, absolute jump, and now possibly what we think might be a call. Because if you look at basically silicon costs money. Unlike a malware VM where they're trying to deter you from analyzing it, the silicon is all about how can I build it in the simplest and cheapest way that it'll work. And an absolute jump is really similar to an absolute call. The only difference is that the absolute call has to push the return address onto the stack. So it makes sense just to have a single bit that says, hey, you're going to have to push the return address when you execute this. And once we have a call, we can find ret and the value for return. And so functions normally look something like this. You've got a function, a return address, followed by another function. And indeed, this is one of the heuristics that was proposed by Chernov and Trozina at REcon 2012, except they were going the other way around, using ret to find call as opposed to vice versa. But unfortunately, a lot of embedded systems aren't quite that simple, or as simple as the picture I've shown. For example, on ARM, you have constant pools where you have read-only data allocated, or in some cases read-write data. I've seen out of one compiler allocated right after the function body, and in some cases you also have alignment bytes, and that might be because the processor requires it, because that's what the ABI calls for, or sometimes that's just what the compiler does for no particularly good reason. So thankfully for us, the ADF 7242 is pretty simple. And so this is a histogram of the byte value immediately before a call target. So you look where a call points and then make a histogram of all of the byte values immediately before that. And there's one byte that sticks out as being by far more prevalent than any other immediately before where a call may point, and that's byte value OXA, which is also the new line or return character. And it's if the analog devices guy that originally built this core is out there, it's particularly nice that you made your return instruction the return character. It's very convenient. So while this works for the naive example here where you don't have any spacing between functions or paddings, a heuristic that works quite well, and I've used on other systems where it was a bit more complex, is to do sort of a weighted histogram where first you eliminate the padding, and you can figure out what that is because the padding is usually the same, and then weight the count of the byte based on how far it was back, so you have like a 10-byte look-back window or something like that before the target, and then weight those in, and that usually ends up with red in the top 3 or so. So that's worth trying as well. But there's other function structure that we can use to our advantage. functions generally need to save and restore callee saved state. And some embedded arcs save it for you, but most are pretty simple. And this is where, on this particular target, that I stopped being able to use fancy histograms and analyses, because the sample size is just too small. Everything just gets lost in the noise floor, and there's no point in looking anymore. But so the save and state is the saving of state is usually something like a push and a pop pair at the start and the end, and some manual analysis, just looking at functions, identifies a pair of byte values that either always occur together or never occur at the start and the end of the instruction. So you have a pretty good clue that that is involved in saving state of some kind. And I'm not going to walk through, the whole trial and error process of this entire core, because A, I don't have the time, and B, you'd all be bored out of your minds. So I'm going to sort of leave the static analysis process here for now, and just touch on a couple other points before I move on to some dynamic stuff. Remember, we can cheat. In the loadable processor module app note that they had for this particular firmware file, it had a number of memory locations, and those memory locations were used to configure the address matching. So you knew that those memory locations would contain an address. And therefore, those addresses or memory locations had to be loaded somewhere inside this so that they could be used. So we can go constant hunting, go hunting for the binary value of the constants of those memory locations, and that's an immediate, real quick jump to move immediate, followed by move register indirect, and you find those right away. And nothing says that the processor has to use the same memory mapping as your external configuration interface does, which is over SPI in this case, but it's unlikely that they would do anything different, because if you do something drastically different, you need two separate sets of address decoders for the same blank of memory, and extra address decoders cost silicon, and silicon costs money. And they're using a custom core in the first place, probably because they want it to be cheap. Or they needed something very high performance that they couldn't do with something off the shelf. So this is the end of what I'll talk about for static methods, but using similar guess and check and validate mechanisms as I described before got us conditional jumps, conditional relative jumps and always relative jumps, absolute call, absolute jump, return, as well as move immediate, register to register transfers, register indirect memory read and write, as well as some ALU operations, which would be add, subtract, compare, bit test, bit clear. And all that came out through sort of guess and check style methodologies. So remember, when you're doing this kind of thing, is that code is sane. Values shouldn't be written to a register and then promptly overwritten. The ALU and registers shouldn't behave in one way for the vast majority of instructions and then differently for one instruction alone. There shouldn't be a huge number of distinct encodings for the same operation that you think is occurring. And values shouldn't be presumed to teleport between registers or from registers to memory or vice versa. Ironically, the ADF 7242 breaks 3 out of those 4 rules, so you can't take them as a hard and fast rule, because this core is very tightly coupled to some hardware around it. But those are some general rules of thumb you can use to figure out if you're on the right track. And in fact, while I was putting this deck together, I was reminded of an attempt to decipher linear A. And linear A is a as yet undeciphered ancient Greek script that was used for writing down their spoken language. And a reviewer of one proposed translation remarked that the quality of a new translation could be judged by how many, or rather how few, new gods hitherto unknown to history that the translation proposes. And I think the same can be said for binary analysis, except replace gods with nops. If you've got 5 or 6 different things that you think are probably a nop, because you can't figure out what else they might be, you're probably on the wrong path. So this is our particular, all you need for a test bench. This is all you need. I've put the DigiKey parts up there if you want it, but you can find them both on Mouse or any other distributor. All you need is an FTDI cable and the little dev board you can get. So it's really easy to hook up to your computer. I've actually got it with me today. If anyone wants to see it after the talk, just come bug me. And as an aside, dumping the internal ROM on this was really, really easy. So this is the documented command set of the SPI interface that you use to interface with the processor. And I sort of wonder what this undocumented area of the command set was, if anyone has any guesses about what that might get one access to. It was very easy to dump the ROM, suffice to say. So moving on to dynamic methods, and I'm going to have to move really fast because I think everyone wants to go for lunch in 6 minutes, and I know I won't keep you through that. It's basically make yourself an oracle and then proceed to query it until you learn all sorts of interesting things. A processor has state, and this is an example of the state that I knew about at the point I stopped my static reversing of it. I had 3 registers of various sizes. I, of course, knew the instruction pointer and the RAM. And when you execute some instruction on the processor, well, obviously something happens to the state. Otherwise, it wouldn't be a very useful instruction. So observing this would be trivial if we had a debugger, because you could just single step it and then dump all the values. But in this case, we don't even know if a debugger exists, and if it does exist, we don't know how to use it. So the goal for a test bench to try and go after these things is to set up as much state as possible on the core using the instructions we already know about, which is move immediate, run an instruction that we don't know what it does, collect all the state that we can, and then compare it to see, compare it against our model of what that instruction should have done. Excuse me. And for the ADF 7242, this looks like just generating a test bench program, compiling it on the host with a little assembler, uploading and running that test bench on the hardware, and that test bench sets up the state with the move immediate instructions, as I said. And then the test bench writes the state to that RAM window that I discussed very briefly because I'm moving pretty quick in this 30 minutes. Writes that state, the host reads it back, and then compares it. And one challenge that you have, especially when you only know a little bit about the processor, is that it can be very hard to retrieve some state without clobbering others. For example, I had found that the processor had a condition flags register because I saw some things working with it, moving nibbles there that were then tested and branched upon. And I knew how to read the condition flags register, but to do so would clobber a register. And similarly, saving that register would trash the condition flags register, so I couldn't get both at the same time. And it's obviously a simple solution to that is just to make two test benches, one that gathers one part of the state, and one that gathers the other, and then put it back together in software so you can see the entire state that changed. And when you run a test bench step like that, you then have to characterize the output. The first output is no effect, and that can be that you're actually an op, but really when you see a whole bunch of things that have no state, it probably means that there is some state that you don't know about. There's something that you haven't realized is in there yet that's actually being changed. Sometimes it's a constant effect, and the most simple of that is a move immediate or a clear instruction, but it also could be unset or unchanged input state. If there's input state that you're not setting up ahead of time and it's always remaining constant under your test bench runs, then that would also appear to be a constant instruction. There's deterministic effects, for example, an ALU operation where you add 2 input registers that you control and you can predict what the output value will be. There are non-deterministic effects, which only appear non-deterministic because hardware usually is deterministic. So unless you think for a good reason that there's RD-RAND or RDTSC equivalents down in your particular target, it probably means there's input state that you're not controlling yet. And finally is a crash condition, and that means that you've either found a new piece of control flow that you don't know what it's doing, or you found an instruction that's either unimplemented that results in a processor hang, or you found something weird, and I'll talk about one of the weird things in this chip that I came across in a little bit. And I strongly recommend building a validation test suite, and that's model each instruction, and then what you do is you have the test suite run such that it compares the execution of the model versus the execution in the hardware. And you should run each test with multiple random input vectors and make sure that you're always predicting the correct output. And something that's really important to do is make sure that you're not trying to predict the entire state, just predict the differentials. So that as you discover new state over time that you don't necessarily know about at the beginning, then you can just rerun the entire test bench with that new state being set up to something random and see if your predictions still hold. For example, that would allow you to detect the difference between an add and an add-C. Initially, you might think they're both add operands, but if there's a carry bit that you don't know to set and you find it later on, then rerunning the test bench will identify, hey, I missed something there, and I should go back and check it. So I'll talk a little bit about the weird and wonderful things I found there. I think I'm down to 1 minute, so I'm going to get through this real quick. It ends up having two separate address spaces. Program memory is addressed with a 13-bit program counter, and data is addressed with an 11-bit data. So the RAM for data storage is an 11-bit address bus. Internally, it has these registers, and these are the ones I know about so far. And I'm fairly certain those are most of them, but you never know with this kind of system. So there's a couple registers which I'm calling general purpose registers, though they're not really general purpose. I don't have a better name for them. There's two 10-bit registers and a 16-bit register. R1 is usually used as the value in a load store operation, whereas R2 is usually used as the address. A and R1 are usually used as a pair for ALU ops. So I'd originally called it A for accumulator, but it turns out not to be that after a bunch more reverse engineering. And there's also two really weird registers, one of which is a packet pointer register, which is a sort of a register indirect access with hardware base offset based on the current packet it's busy spitting out the RF transmitter. And there's also a specialized loop counter register, which is only ever used by three instructions, which is set loop counter, read loop counter, and decrement and jump if not 0. So that particular register isn't touched by anything else. So it's sort of weird down at the instruction set level. But it gets weirder. There's some directly coupled I/O instructions. For example, there's an instruction that appears to allow turning on and off the power amplifier or setting it to a particular level. There's an instruction that directly enqueues some bits to be transmitted. And there's also blocking instructions to match those. For example, block the core until this particular hardware function completes, like, for example, transmitting a byte out the RF port. And ironically, because of the way that's built and it's encoded, you can actually block the core until any condition bit is set. So you can actually do block until not 0, which is not a operand you ever find in the disassembled binary because it's not terribly useful. Once the core is halted, waiting for it to become non-zero, nothing's ever going to make it non-zero. There's also specialized communications instructions, for example, bit reverse and CRC baked in. And you see a lot of these kind of weird instructions in these special purpose processors. In other ones I've looked at, I've seen instructions for accelerating S-boxes for cryptography, Viterbi decode acceleration, bit shuffle and extract, stuff for accelerating forward error correction. So there's a lot of really interesting things you find down there. And so the state of the tools today for this particular core, I have a disassembler that covers the vast majority of the instruction space. The ones that I don't know about never appear in the disassembly I have. So the best guess I have is that they're either unimplemented, encoding space, or they do something that I haven't found state for yet. I have a basic assembler, and as well as the disassembler, of course, and a loader and I/O library for playing with this thing. And I'm going to post it soon at github.com/davidkarn. It's not going to be while I'm at REcon because I didn't bring my SSH keys. So thanks for coming out to listen, and I guess any questions, or does everyone just want to leave for lunch? Lunch it is.